Today we're going to look at the relationship between independence and expectation and variance of random variables. So in a nutshell, the important formula which we are going to prove is that if we have two independent random variables and we multiply them, then the expectation of the product is the product of the expectations. And if you think about it, if you remember the definition of the expectation, it is simply the Lebesgue integral. And if we go back into measure theory, then what is written here is something like saying that the integral of the product of two functions with respect to some measure is equal to the integral of the first function times the integral of the second function. And by no means would you expect something like this to happen generally. But it does happen for independent random variables, and this is why the analysis of them is so elegant. And in particular, later on, we will define characteristic functions, which will be an extremely powerful tool, in particular to study independent random variables. And most of the power comes from this property, this multiplicativity property for independent random variables. So the theorem is important, but the proof is quite simple. But before we do the proof, we need a precise statement. So let's start by saying let x and y be independent random variables. So the first part of the theorem says that if x and y both are integrable, then the product is also integrable. So is xy, and the expectation of x times y is equal to the expectation of x times the expectation of y. And the second formula is about variances, but now I need to assume that x and y have variances, so they are square integrable. So if x and y are square integrable, then so is their sum, x plus y, and the formula which I'm going to write down is the additivity property for the variance. So I'm going to say that the variance of x plus y is equal to the variance of x plus the variance of y. And I don't want to have two parts A in here, so this should clearly be part B. Now, this formula will follow very easily from this one. Therefore, I mean, it is important, but it is very closely related to this one anyway. So let's concentrate on proving this one. And since we are proving something about expectations, we will use the same method as usual. So we will first prove the formula for the indicators, then for simple functions, then for non-negative functions, and finally for all functions. So proof, so I call it step 0. Suppose my x is an indicator function and my y is an indicator function of another set. So both sets belong to the underlying sigma algebra in our probability space where everything is defined. Now, since x and y are independent, the sigma algebras are independent, and the sigma algebra of x is simply consisting of 4 sets, because my x is so simple, right? It has such a simple structure. So it will consist of the set A, of the set omega minus A, omega, and the empty set. And the sigma algebra of Y very similarly will consist of B, omega minus B, omega, and the empty set. And those are independent, which we know simply means the product formula for the two sets A and B. We know if we have that, then the product formula for all other pairs of sets will follow. Fine. Now let's start with the left-hand side here. So the expectation of xy is equal to the expectation. So x is the indicator function of A, y is the indicator function of B. What happens if I take the product of two indicator functions? I get the indicator function of the intersection. So I have the the expectation of the indicator function of A intersected with B. How do I compute the expectation of an indicator function? It is simply 1 multiplied by the probability of the intersection. And now you see why I wanted to have this formula first, because I'm going to use it here. And then basically bring everything back. So I'm going now to say that the probability of A is the same as the expectation of the indicator function of A. The probability of B is the same as the expectation of the indicator function of B. And those are X and Y. So I get the formula which I wanted. Now let's see what happens with simple functions. Usually we say it follows by linearity because the left-hand side and the right-hand side of what we want to prove is linear. This is actually not the case for this formula. It is not linear. So if I substitute x1 plus x2 here and y1 plus y2 here, I mean, it has two parameters. We can't talk about linearity. But it is bilinear, which is fine. So this part is bilinear, this part is bilinear. And therefore, if I substitute a simple function for x, which is a linear combination of indicators, and a simple function for y, which would be also a linear combination of indicators, then I can follow the bilinearity rules for both sides, and this will boil everything down to this formula for the indicators, which we have proven in step 0. So I don't need to do much in step 1, except maybe saying that so for simple functions, so for simple x and y, we use bilinearity of, let me denote it by star, by this star here. Now, if I want to extend it to non-negative functions, so for x greater or equal than 0 and y greater or equal than 0, nothing changes. I still approximate them from below by simple functions and use the monotone convergence theorem. We use monotone convergence theorem as before, so as usual. And finally, for arbitrary functions, so for any x, y, we use this decomposition as we would normally do. But since we will substitute both terms into star, it's again the bilinearity which we need, not linearity. So let me say, and again bilinearity. So that finishes the proof of the multiplicative property. And now let's quickly do the variance. So this is very simple. We want to prove that the variance of x plus y, let me put it somewhere at the end, is equal to the variance of x plus the variance of y. What is the variance of x plus y? It's the expectation of x plus y squared minus the expectation of x plus y squared. I will multiply everything out. So from the first term, I get the expectation of x squared plus 2 expectations of xy plus expectation of y squared. From the second term, I get the following. So this thing I can write as the expectation of x plus the expectation of y. This is the linearity of expectation. And then when I square it, I get 3 terms as usual. So I get minus expectation of x squared minus twice the product, so the expectation of x times the expectation of y minus the expectation of y squared. And you see what is going to happen. I'm going to use the multiplicative property. I'm going to say that this expectation we have just proved is equal to this product here, and therefore they cancel out. And then I'm going to say that those terms together give me the variance of x, so this term, and those terms together give me the variance of y. So this is how I get this thing here. So this is very simple indeed. So this is the second part. Now, we will see powerful applications of that later on, but at the moment, let's look at a simple example. Let's talk about a binomial random variable with parameters n and p. So let me call it x, and one way of defining it would be as a sum of n Bernoulli random variables with parameter p, so of independent Bernoulli random variables. So this one and all of them are independent Bernoulli with parameter p. Now, suppose I want to compute the expectation and variance of the binomial random variable x. The straightforward way would be to calculate the probability distribution of x, which means calculating all those probabilities, which you know are not that simple, which would take some time, and then compute the expectation by multiplying those probabilities by k and summing over all k. And then, even worse, for the variance, we would have to compute the second moment, and so on and so forth. Now, if we are not interested in probabilities, but are only interested in the expectation and variance, we can forget this, and we can compute those directly. We can say, well, the expectation of x, I don't even need this theorem here, it's just a linearity property, is equal to the expectation of x1 plus the expectation of xn. All those expectations are equal to p, so I get n times p. And for the variance, so the variance of x is equal to the variance of x1 plus the variance of xn. Now, all the variances are the same, therefore I can put an n here. And what would be each variance equal to? So let's look at this one. So it would be the expectation of x1 squared minus the expectation of x1 squared. So if I square a Bernoulli random variable, it's still a Bernoulli random variable with the same parameter. So the first expectation is p, but now I need to square that expectation, which gives me minus p squared. So this means that I can write it as p1 minus p in here. So this is p1 minus p. So even in such a simple example, this formula, this multiplicative property, can save us quite a lot of time.